So, in this lecture, we will get acquainted with neural connections, activation functions, and layers. Let's recall the neurons model that was introduced by Warren McCulloch and Walter Pitts. The signal that neuron transmits can be described by this equation. X with index j is input information, and here you can see weight with index j and bias. They will be adjusted through the learning using a backpropagation method. Bias is a free input, and we will discuss it at the seminar. It doesn't depend on the signal. Then we want to get a sum, apply activation function, and calculate resulting signal y. Layer of the neural network is not only a group of neurons. It consists of the preceding connections and neurons to which these connections come. Through the learning, only connections are changing. There are weights that are trained. We will look at the layers in more detail a bit later. As I have already said in the last lecture, a basic activation function is a threshold. It is not suitable for complex machine learning tasks. It is good only for classification. It has a gap, while a propagation method requires an information about derivative, and it is better to have a certain derivative at each point of the activation function. That's why we can take a linear function, for example, where the derivative is simple. The simpler the derivative, the quicker the learning process is. It is suitable for classification and regression problems. We can divide our linear function with a certain threshold into two parts, and the first part will belong to the first class and the second part will belong to the second class. What about regression? Linear function is continuous and it is possible to map it into different continuous sets of answers. However, linearity is not a universal tool for machine learning problems. If the solution is described by nonlinear function, it is impossible to approximate it with a linear one. What's more, derivative of the linear function doesn't depend on input signal. Backpropagation method will change the value of weights with a certain constant step at each iteration of the learning process. Actually, it is not good. To find nonlinear approximation, sigmoid function can be used. The derivative depends on the signal, so it is suitable for complex classification and regression tasks. However, derivative calculation is an expensive process because this function is complex and it takes a lot of time to calculate a Taylor series expansion of sigmoid function. There is an analog to sigmoid function, but with different boundaries. It is Tank function that returns values from -1 to 1. These types of activation functions are really useful, especially sigmoid function. But troubles with calculating derivatives leads us to the next type, ReLU function. So, at x bigger than 0, the derivative of this function will be a constant. In another case, it will be a 0. It turns out that the derivative is simple. However, this activation function has disadvantages too. With negative signal, neurons are not trained. That's why we will move to the leaky ReLU. That is the most suitable activation function. It is similar to ReLU, and adding a small extra coefficient to the part of function that describes the behavior of leaky ReLU at x less than 0 helps to solve the problem of dying neurons. To sum up, the main advantages of activation functions are nonlinearity and an ease in derivative calculation. You can try your own activation function that will be useful for your own tasks. It is okay. Let's move from the neurons themselves to neural networks and talk about fully connected NNs. This structure connects every preceding neuron with the next one. Every connection contains its own weight. In this way, if you have n neurons in the first layer and m neurons in the second one, and these two layers belong to the VCN, the number of weights will be a product of m and n respectively. The main feature of VCNs is dividing. So one neuron can divide an area into two parts, and combination of neurons can extract more complex shapes. For example, the VCN with 2 layers can extract convex polyhedral areas, and VCNs with 3 layers can extract non-convex disconnected polyhedral areas. In this way, we can divide our data into groups, thus solving a classification problem. In the simplest case, to divide into two classes, it is required to approximate the line which will be the boundary between two classes of points. Adding a layer complicates geometric objects which divide your data respectively. The second type of neural networks is recurrent NNs. It differs in the structure of neurons' connections. The signal can propagate not only forward but also in the another direction, in the opposite direction. At this example, the neuron's output is connected to its input. These structures are used in tasks where the preceding signal depends on the resulting one. It is successfully used in time series tasks. For example, audio recognition and video analysis, where the system evolves. Up to this point, we have always talked about the uniqueness of the neuron's output. However, to solve some machine learning problems, a structure with multiple outputs is used. For example, there are a lot of classes in a classification problem, and using multiple output structures gives an opportunity to assign each class to each output. What's more, you can normalize every network's output and map it into a continuous range of numbers from 0 to 1. This gives you an opportunity to perceive the network's answers as the probability of belonging to each class. This approach is really useful in models for classification. Let's look at the example. Here you can see a picture with bicycle. You can see the result, how normalization is working. The highest probability is belonging to the class of bicycle, respectively. In the first two lectures, we got acquainted with neural networks and with the concepts of machine learning. However, I have not mentioned a single proof of operability of all these methods. Why we think that neural networks can approximate the functions that described solution of these problems. All this theory works, and the cause of it is the Tsybinka theorem. It says that a continuous function could be approximated by a neural network. So that's all I wanted to say. Goodbye.